Hi, welcome to this lecture in our theory of equations course. This is an important topic here where we talk about irreducible polynomials. We'll also be looking at several criteria by which you can decide if some polynomial is irreducible or not. So there are Maths Olympiad questions which test your knowledge of this principle. So let's get into it. First of all, I want to get our terms right, like what is an irreducible polynomial in case you're not aware. An irreducible integer polynomial is basically a polynomial that has no factors. So no smaller polynomials are going to be factors of it. So I'll just write the definition formally. Polynomial P is one whose only integer polynomial factors are plus minus 1 and plus minus p. So what do we mean by this? So first of all, notice that we are talking only about integer polynomials. So what is an integer polynomial? One where all the coefficients are integers, right? So an irreducible integer polynomial P is one whose only integer polynomial factors are this and this. So examples could be, let's say, x squared plus x plus 1. You cannot split it. You cannot split it like this to make it an integer polynomial, right? Like, because this has complex roots, so there are no possible factors like this. So no integer polynomials are factors of this other than except plus minus 1, which is a degree 0 polynomial, and plus minus p itself, right? So that is the definition. Now, basically, let's write down, we can say that any integer polynomial can be now written, any integer polynomial px can be eventually factorized and written as a product of some irreducible polynomials, right? Any integer polynomial p can be written as, px can be written as qx multiplied by hx, where hx and qx are basically irreducible integer polynomials. So notice that there is a strong similarity here between polynomials and number theory. So these irreducible polynomials are like prime numbers, right? Prime numbers have no other factors except 1 and themselves. Similarly, these irreducible polynomials have no other factors other than themselves and 1. So this statement is basically the prime number theorem, which says that any number can be written as a product of primes, right? Here we are saying any polynomial should be expressed or can be expressed as a product of multiple irreducible polynomials, right? So this is this theorem. And obviously, now we know from here that any roots of q and h will be roots of p, So that is obvious from this statement when px is written as qx into hx, right? So let's get started and let's think about irreducibility a little bit. I will start off with an example problem. So example question is this: prove that a quadratic polynomial with odd coefficients is irreducible. Odd coefficients is irreducible. So let's try to prove this. A quadratic polynomial will look like this: ax squared plus bx plus c. And we have to prove that it is irreducible. So let's prove by contradiction. So by contradiction, basically what we are saying is, let's assume that this is reducible. Here what we have is a, b, c are odd, correct? So let's assume that this ax squared plus bx plus c is reducible. So we should be able to write ax squared plus bx plus c as a times x minus r and x minus s, right? assuming x minus r and x minus s are the factors. X minus s are integer polynomials and they are factors. Correct? So we have assumed the opposite. We are saying that it is reducible. Then we have to show a contradiction here, right? So if we compare coefficients, we get ax square minus ax plus a r plus s into x plus rs into a. This is the polynomial that comes this side, and this side we have ax square plus bx plus c, right? These polynomials must be equivalent. So basically we should have a into r plus s should be equal to b, right? Minus of a into r plus s should be equal to b, correct? And we have also a into r plus s, a into rs should be equal to c, right? So now what does this mean? Now imagine from here what we are getting, c is odd, a is odd, right? So therefore you have rs is also odd, right? Because if rs was even, even multiplied by odd would become even, and c is actually odd, right? RHS is odd, so LHS must be odd, so RS must be odd. And if RS is odd, means R and S are both odd. Correct? R and S are both odd. That implies that R plus S is even, right? R plus S is even. And now if this part becomes even and this is odd, then the product becomes even, but that means that B was odd, right? So this is a contradiction. Even is equal to odd is happening. So basically a contradiction has been established. So what we have basically said is that this cannot be factorized like this. This is not possible. So basically we get that this is irreducible now. Correct? This quadratic polynomial cannot be broken down into linear factors. So it is an irreducible polynomial. So you should sort of get a sense of what it means for a polynomial to be irreducible right now. Now, what you look at is several interesting criteria for checking this fact, right? So the first criteria that we look at is called the Eisenstein's criteria. Eisenstein's criteria for irreducibility. So what is this? So suppose we have the following polynomial. We have px is equal to an x power n plus an minus 1 x power n minus 1 plus so on plus a1x plus a naught, right? Now this is an integer polynomial, suppose. So integer polynomial basically means that a naught, an minus 1, a1, a0, all of them are integers, right? Now if there exists a prime p, prime number p, such that the following three conditions are true. First condition is p does not divide an. P does not divide an, right? The second condition is p square does not divide a0. So p does not divide the first coefficient and p square does not divide the last coefficient. And the final condition is p divides ai for all I not equal to n. Basically, this means p divides all other coefficients. All other coefficients. Okay. So then that means if these three conditions are satisfied for a prime p, then it implies that p of x is irreducible. This is the Eisenstein criterion. Now, can we see an example where all of this happens? So let's write an example. Please note down this criteria. This is super important. So pause the video, take it down, make sure that you understand what we are saying. It is very simple also to understand. It says that you have to find a prime p which divides all the terms in the middle, does not divide the first term, and p square does not divide the last term. If that is true, then that polynomial is irreducible. So let's see an example quickly. So prove that, question is prove that x power 7 plus 5x power 4 plus 35 is irreducible. So the obvious candidate here is take prime number 5. So we can see that 5 divides 5, right? But 5 does not divide 1 and 5 squared does not divide 35, right? 5 square is 25. 25 does not divide 35 and 5 does not divide 1. So these are the first two criteria. And this is the last condition. All the other coefficients are divisible by 5. So by Eisenstein, we know that this polynomial cannot be factorized any further into integer polynomials. This is irreducible, right? So that is a simple way in which you can test if a function is irreducible or not, right? Let's go to the next example and the next criteria actually. The second criteria is Cohn's irreducibility criteria. Cohn's irreducibility criteria. Now this is quite interesting because you would not expect this type of thing to happen. Right now we are not doing proofs of Eisenstein and Cohn's and also the third criteria, Perron. In a later video, if you guys are interested in the proofs, I might look at providing the proofs, but right now we are not going to look at the proofs. Proofs are slightly advanced. So Cohn's criteria says this: given a prime P whose base 10 representation is an 10 power n plus an minus 1 10 power n minus 1 plus so on plus a1 10 power 1 plus a0 10 power 0, right? Where each ai 0 is less than equal to ai is less than equal to 9, because it is a base 10 representation of p. P is equal to this, right? The polynomial p of x is equal to an x power n plus an minus 1 x power n minus 1 and so on till a1x plus a0 is irreducible. So what is this? What is this happen here? So basically you're saying that if you can write p, a prime number p, in a base 10, if you can write it as an 10 power n plus an minus 1 10 power n minus 1 and so on, then this polynomial is irreducible. Let's see an example to understand what is happening. Suppose you have to prove that polynomial px is equal to x cube plus 7x square plus 3x plus 3 is irreducible, right? So let me just try to think about base 10 representation of these coefficients. So we have 1, 7, 3, 3 as the 4 coefficients. So let's construct the number 1 into 10 power 3 plus 7 into 10 square plus 3 into 10 plus 3 into 10 power 0, right? This number is basically 1733, right? Because 3 into 3 comes here and 30 and yeah, 1733. So basically the coefficients of the equation are the base 10 representation of 1733, right? 1733 in base 10 is basically the coefficients 1733, right? Now, if 1733 is a prime, if it is a prime, then this polynomial is irreducible. That is the Cohn's criteria. Now check whether 1733 is a prime or not. It is indeed a prime number. You can check that yourself. 1733, you can check all the factors from 1 to root of 1733. All the prime numbers from this you can check. It will not be divisible by any of them. Therefore, it is a prime. And therefore, this p of x is irreducible by the Cohn's criteria, right? So we have two criteria right now, Eisenstein and Cohn. Let's do a question where we apply this. So the question is this: if f of x is equal to x power p minus 1 plus x power p minus 2 and so on till x plus 1, where P is prime. P is prime. Right? Now you have to prove that f of x plus 1 is irreducible. Is irreducible. So what we will do here is we'll first try to understand what is f of x plus 1, and then we'll think about the irreducibility of it, right? So first of all, this series seems very familiar to us. Like I have seen this type of an expansion before, like x square plus x plus 1, or x cube plus x square plus x plus 1. I know that this is like a GP, right? This is a GP of 1x x square. So I can write GP formula and I write this like this, right? Sum of the GP, right? So I can write this like x power 4 minus 1 by x minus 1. So similarly, f of x can be easily written as f of x is equal to x power p minus 1 plus x power p minus 2 and so on, right? Till x plus 1, that can easily be written as basically x power p minus 1 by x minus 1, right? So what about f of x plus 1 now? If I put f of x plus 1 here, it will become x plus 1 power p minus 1 by x plus 1 minus 1. So that is simply x plus 1 power p minus 1 by x, right? Great. So we have understood what the f of x plus 1 polynomial is, right? So if you write the terms of this polynomial, let's try to write the terms for a bit and see what comes, right? So notice that the first term, when you do an expansion of 1 plus x power p, it will become 1 plus x plus pc1 into x plus pc2 into x square and so on till x power p. So when you subtract 1 from this, it will just be pc1x plus pc2x square plus so on till x power p, right? And if you divide the whole thing by x, that is what we have to get here. So that polynomial will be pc1 plus pc2x plus pc3x square, so on, till x power p minus 1, right? X power p minus 1. Last term will become that. And notice the second last term. Second last term would have been pc p minus 1 x power p minus 1. So the second pcp minus 1 is simply p. So the second last term here, I will write here, is p x power p minus 2, right? Great. So I'll just write it in the next screen to make it clearer. So f of x plus 1 is coming out to be x power p minus 1 plus p x power p minus 2 and so on till pc2 x power p minus 3 plus pc1 x power p minus 2. No, not p minus 2. This is wrong. This will be x power 3. This is x square and this is x. And finally, there is 1. Right? Okay, I have forgotten what I wrote earlier. 1 second, I'll just go back once and I'll see what was coming there. We'll probably do it on the same screen as before. So let me just go back. Okay, so this is my expression. I will just solve it here. So let's see. So I'll just write your f of x plus 1 here itself. It is becoming pc1, first term is p, then pc2x plus pc3x square and so on. Second last term is p into x power p minus 2 and last term is x power p minus 1. Great. Now I have the function here. How did I get it? I got it by noticing that f of x is a GP sum and then f of x plus 1 is replacing x for x plus 1 in the GP formula. Okay. Now, and then using binomial theorem. Now let's check Eisenstein. So since p is given to be prime, we have to check that the prime number p does not divide the highest power coefficient, does not divide basically an, p square should not divide a naught, and p should divide everything else, should divide all other coefficients. So here you can clearly see that p does not divide 1, the coefficient is 1 here. Also, p square does not divide p, the last coefficient is p. P divides p, but p square does not divide p. And finally, you can see that all the terms here are basically PC1, PC2, PC3, and so on. And if you write the expansions of these terms, you'll always have a p term here, because PC1 is p, PC2 is p into p minus 1 by 2, PC3 is p into p minus 1 into p minus 2 by 3 factorial. So every time all of these terms are divisible by p, right? So this satisfies all the three criteria for Eisenstein, right? And that ensures that this f of x plus 1 is irreducible, right? So very easy solution if you know what you're doing and if you know Eisenstein criteria, right? Let's get to the next one, the last criteria, and this is quite powerful. This is called Perron's criteria, Perron's irreducibility criteria. Let's first understand the criteria here. There are two equivalent statements here, two statements. So what we'll say is, given p of x is equal to an x power n plus an minus 1 x power n minus 1 and so on till a0, right? P of x is irreducible. P of x is irreducible if you have mod of a naught is bigger than mod of a1 plus mod of a2 plus mod of an, when mod of a naught is a prime, So this is the first version of our criteria. It says that if mod of a naught is a prime number and it is bigger than the sum of all other mods, right, in the polynomial, then px is irreducible, right? The second version of it is somewhat more useful in problems, so we'll write that as well. Suppose px is given as x power n plus an minus 1 x power n minus 1 and so on till a naught, right? Now the condition is px is irreducible. Px is irreducible if mod of a n minus 1 is greater than mod of a naught plus mod of a1 plus so on till mod of a n minus 2 plus 1, right? And a naught should not be equal to 0. Basically, in the second version, you have two conditions. One condition is a naught should not be 0, and the second condition is the second highest coefficient, the mod of that, should be greater than the sum of all the other coefficients. Notice that all the other coefficients are coming here, no? Till an minus 2 would be here, and 1 is the coefficient of this, right? So what is this criteria? You should have a naught not equal to 0, and a of n minus 1 mod should be equal to, or should be greater than the sum of all the other mods, all the other coefficients mods. Then the polynomial is irreducible. However, notice that this is only valid when the first coefficient is 1. If you have this type of situation when the first coefficient is not 1, you should use the first version of the criteria. So that is irreducible if the last term's mod is greater than every other term's mods, sum of all of them, and a naught mod is also a prime. So it might be tricky and confusing right now, but we will solve some problems with it as we go along, and we will see how this solves many questions. So for example, there is a USA Maths Olympiad problem in 2007, which was stated like this. It says, show that for any function f, for any f with integer coefficients, coefficients that is non-constant. So basically it's not a constant polynomial, non-constant. There are infinitely many integers n such that f plus n is irreducible. F plus n is irreducible. Okay, so it can be easily proved by Perron's criteria. So suppose we take f to look like this: x power n. Actually, you should write it an x power n and an x power n plus an minus 1 x power n minus 1 and so on till a naught, right? So by the first version of the criteria, if this is a non-constant polynomial, so we should have mod of a naught should be prime and mod of a naught should be greater than mod of a1 plus mod of a2 till mod of an, right? Till mod of an. These two conditions should be true for f to be irreducible. That was Perron's criteria. Now we have to do this for polynomial f plus n. So it is basically an xn plus an minus 1 xn minus 1. So 1 plus a naught plus n, right? So this is my new a naught, right? This is my new a naught for this polynomial. So what you have to ensure is that a naught plus n is a prime number. So you have to take a naught plus n as a prime number and basically pick a large enough prime so that it is bigger than the mods of all of the rest, right? So you have to show that mod of a naught plus n is greater than mod of a1 plus mod of a2 plus so on mod of n, and this part is adding up to be a prime number, right? So obviously there will be one prime number. So what is the value of n that is needed here, right? So we just have to ensure that a naught plus n is a prime. So you can pick some prime q. A naught plus n is equal to q. Q is a prime number. N should be q minus a naught, right? Right? And q is large enough that it is bigger than the sum of all of this, right? So there will be a possibility to find a q which will be large enough, which will be bigger than the sums of all of this, right? Basically find the sum of all of this and find the next prime number and choose n to be q minus a naught, right? And all higher primes after that will definitely satisfy this. So immediately by Perron's criteria, every polynomial like this will be irreducible as long as you ensure that this sum is lesser than prime number and the prime number is equal to a naught plus n, right? So you have to pick a prime number which is q minus a naught for n, right? So I hope you understand what is happening. You are picking an n which is q minus a naught, where q is a prime number such that it is greater than the sum of mods of all of these terms, right? Once you have done that, you can always say that for any higher prime number higher than q, it will automatically satisfy by Perron's criteria that f plus n is irreducible. And because prime numbers are infinite, you can keep taking higher and higher prime numbers, and this will be true. So you should keep in mind that these criteria are super powerful. I will be able to show you a proof of Perron's in a future video. And once you know how it comes, and once you have learned how to apply this in problems, it kills many problems very easily. There are difficult irreducibility problems that can be asked, and all of it will be easily resolved by at least one of the three criteria that we have seen: Eisenstein or Cohn or Perron's. So that's all for this video. I hope you learned something new today. We'll come back with more videos on polynomials and questions. See you next time.